Now we know how PCA works, and in this slide, we're going to talk about some extensions from PCA. So PCA is unsupervised learning, and it is linear, and it is based on the eigendecomposition, which is based on the uncorrelatedness. Okay, first extension is about the supervised learning. So in PCA, we didn't use any labels, but for projection, we can use labels at the same time. So we are going to talk about LDA, linear discriminant analysis. And then if we extend the PCA based on independent factors, which is more than just uncorrelatedness, then we can talk about ICA, independent component analysis. And these are still linear method, linear projection. And we can think of nonlinear mapping. And in the nonlinear mapping, we can talk about the kernel PCA, or we have lots of other manifold learning algorithms. So in this chapter, still we will focus on the linear method. So to extend PCA with supervised learning, we can talk about LDA. And to generalize uncorrelatedness to independence, then we can think of ICA. So first, we're going to talk about labels with linear mapping. So first of all, the dimensions of largest variance are good. This one is about the PCA. Okay, so in the PCA, we actually prefer the largest variance in the projected space. Okay, that is good, but that's not always the best. Sometimes we might have a better linear mapping. So the PCA could be unwise from a classification point of view. As I said, in the PCA we don't use labels. But what if we have labels? So in the PCA we cannot use class label information. In the PCA, the discriminant dimensions might be thrown out because PCA is focusing on just largest variance. So let's take an example here. So we have lots of samples, and in PCA, we have no idea about the labels. So we just consider all the samples as just one set, okay? And then PCA focus on the variance. So PCA prefer this line. So all the points will be projected onto this line. Look at this one. This one is from -5 to 5. This one is from -2 to 1.5. So this one is actually the long in this direction. So PCA prefers this direction. But if we look at the labels, then this direction is not the best direction. So look at this one. So all the samples are projected onto this line. And then on this line, these blue dots and the red dots are just mixed up. So if we are interested in classification, then this line is the worst direction. Instead, we might like this direction more, because in this line, if we project all the samples in this line, then we have lots of blue dots here, and we have lots of red dots here. So in terms of classification, this line is way much better than this PCA direction. Okay, so here is another example. It's basically the same thing. We have the digits in a two-dimensional space, and the PCA prefers this direction. So we project all the samples onto this line. And then as you can see here, the green one, which is a digit 1, might have this distribution, and the red one has this distribution. Okay, so we cannot distinguish 1 and 2 in this dimension, but in LDA, we project the samples onto this line. So as you can see here, we can classify these digits based on these dimensions. So if we draw a line here, then the left side is class 1 and right side is class 2. So in this case, instead of preserving the largest variance, we give up that, but instead we actually focus on the classification part. Okay, so let's talk about some LDA equations. LDA is actually also known as Fisher discriminant analysis after Ronald Fisher. Okay, for two-class problem, we can formulate the equation in this slide. So we have n samples, and we have class 1 and the class 2. In class 1, we have n sub 1 samples, and in class 2, we have n sub 2 samples. And we can define the class mean and global mean. So this is class mean. It is the mean in the class. N sub I is the number of samples in the class, and we sum all the samples in the class. Okay, and then M is global mean, so we just take an average of all the samples. And if the projection is given by this one, still we are talking about the linear mapping. Okay, so if it is a linear mapping, no matter what kind of objective function, then how you do, the projection is something like this. W transpose X. Okay, and then M sub I tilde is class mean on the projected space. Okay, and this one can be defined in this way. So we get all the samples in the class, and then we take an average, and then Y is W transpose X. So instead of using Y, we can use W transpose X. And then W has nothing to do with this summation, so we can move here. And then if you focus this term, that is exactly the same as M sub I. So M sub I tilde is W transpose times M sub I. Because it is a linear mapping, when we project all the samples with W transpose, and the projected mean is also projected by W transpose. And S sub I tilde square is class variance on the projected space that can be calculated in this way. And then now we want to define the objective function for LDA. Okay, so in the objective function, we want to maximize the ratio of the variance between classes to the one within the classes on the projected space. So in PCA, we try to maximize the variance between the samples on the projected space. Okay, so this part is the same. But we focused on the variance between all the samples in PCA. But in LDA, we try to maximize the variance between the classes. So actually class means. And also we want to minimize the variance within the classes. So we have to maximize and minimize at the same time. So instead of maximizing, minimizing at the same time, we just use the ratio of this one and this one. So by maximizing the variance between classes, we want to maximize this distance between the classes on the projected space. And then we want to minimize the variance within the classes, which means we want to minimize this variance and this variance. That makes sense. Okay, so that's the objective of LDA. So then how can we define this objective with equations? First, this is a ratio. Okay, so we have variance between the classes, and then the variance within the classes. And the variance between classes is actually the distance between the mean vectors on the projective space. And then the variance within the classes is actually S sub 1 tilde square plus S sub 2 tilde square. So this one is the variance within the first class, and this one is the variance within the second class. Okay, so now we defined this objective, and then if you follow these equations, it's a simple equations. So this one can be rewritten by this, and this one, this S sub I tilde square is this one. So we can rewrite this term with S1 plus S2 W. And since SW is actually S1 plus S2, so we can rewrite this term like this. Okay, and then SB is M1 minus M2 times M1 minus M2 transpose. So in this matrix, the rank is at most 1. That is important to think here. So this one is a vector and this one is another vector. So this is one vector. Let's say this one is V. And SB is actually V times V transpose. So we have only one vector here. So even though we have a matrix, this is a matrix, right? So if we multiply these two vectors, then we have a matrix. But still, in this matrix, the rank is just 1. And LDA is actually a generalized eigenvalue problem. So in PCA, the problem was just eigendecomposition, right? But in LDA, we have numerator and denominator. So if we have lambda here, which is a Rayleigh quotient, then we take a derivative of this objective function with respect to w, then we set it to 0, then this is what we have. Okay, and then we can rearrange the terms on the left side and right side. And if S sub w is invertible, then this is what we have. So in this case, this is one matrix. Let's say this is M. And this is just eigendecomposition problem. But if SW is not invertible, then we need some trick. Like easily, we can add some epsilon times identity matrix. So if we increase epsilon, then at some point, this one becomes invertible. That's a simple kind of remedy when SW is not invertible. Okay, when we have only two classes for LDA, then actually we don't need eigendecomposition, because if we have only two classes, then the solution is much simpler. Okay, so let's derive some equations here. S sub b times w, and this is S sub b and this is w. And if we do some calculations by rearranging the terms, and then finally we have this. As you can see, this one is a scalar and this one is also scalar. Look at this one, W transpose M sub 1. So this one is vector and this one is vector. So if we take an inner product between these two vectors, then that is a scalar. So this one is a scalar and this one is a scalar. So transpose means nothing. So this is a scalar. Let's say this one is kappa. Then S sub b times W is kappa times M1 minus M2. So which means S sub b times W is in the direction of M1 minus M2. So in the previous slide, our solution is this, right? So usually we have to apply some eigendecomposition, but S sub b times W is kappa times M1 minus M2. So if we replace this part with this term, then we got this one. Okay, then what we are interested in is W. Then the W is kappa over lambda times SW inverse times M1 minus M2. So as long as we can get this SW inverse, okay, then it's simple. And also, W is a vector, and because we're interested in just the direction, so we can just normalize W. So we can ignore this kappa and lambda. So this is W. Okay, for a Fisher linear discriminant, when we have two classes, then W is this. And usually we normalize W because we are just interested in the direction. Okay, So we talked about the 2-class problem, but what if we have 3 classes or 10 classes? Then we can generalize LDA for multi-classes here. So the objective function is exactly the same as before, but SB and SW would be slightly different. For binary class, we have SB defined by this and SW defined by this because we have only 2. So in between scatter, we are just interested in difference between M1 and M2 because we have only 2 classes. But for multi-class case, SB is defined by this. So let's say we have 3 classes, then this one is M1 and M2 and M3. So instead of the distances between all the mean vectors, we have global mean here. Then we are interested in these distances. So in this case, when we have just the 3 classes, then there is no significant difference because in this case we have a 3 difference and in this case we have 3 difference. But when we have like 100 classes, if we check the distance between all the pairs of mean vectors, then 100 combination, 99 cases. That is huge. But if we just calculate the distance between individual class mean and the global mean, and individual class mean and global mean, then instead of 100 combination 99, we can have just 100 distances. That's why we define SB in this way. This is global mean and this one is class mean. Check this SB and this SB for multi-class case. It's slightly different, but basically the concept is the same. Okay, and then the rank is at most C-1 here. So why the rank is at most C-1? So think about this one. If we have 2 points, then we can define just 1 dimension, right? Like this. If we have 3 points, then we can define 2 dimensions. When we have 4 samples, then at most we can define 3 dimensions. Something like that. So the rank of SB is at most C-1. And SW is almost the same. So for binary case, we have S1 and S2, but instead of S1 and S2, we can just generalize for C classes like this. So as I said here, LDA finds at most C-1 dimensions. So when the samples are in the high dimensional space, like 1,000 dimensional space, but if we have just 10 classes, like MNIST data, then when we apply the LDA, then we can find just 9 dimensions because we have 10 classes. Okay, so don't try to find like 100 dimensions after LDA. That is the maximum dimension after LDA. So when we apply PCA and LDA on the same dataset, then we can compare PCA and LDA. So we actually trained the deep neural network, and then we got the last layer representations of MNIST test data. You don't have to worry about these things, okay? So we got some data, and then we apply the PCA to get the 2-dimensional representation, and we apply the LDA to the same dataset to get 2-dimensional representation. And then as you can see, in PCA, some classes are overlapping here, and in LDA, there are some overlaps, but still, compared to the PCA result, LDA is more distinguishable. That's the beauty of LDA.